In this video, we will learn about nuclear chemistry, modes of radioactive decay, and nuclear equations. So, radioactivity is defined as the emission of tiny energetic particles from the nuclei of unstable atoms. And so, if we say the term nuclide, it's referring to the nucleus of a specific atom. And if you look on the periodic table, all nuclides, so all atoms, all elements with atomic number 84 or more are radioactive. You can tell that they're radioactive by looking at the mass numbers. The atomic masses. The atomic masses are usually written in parentheses because those elements are so unstable that their actual masses cannot be measured. They have to be estimated, back calculated based on the decay products. So what's happening here? So let's do a brief review of our atomic symbols from way back in the beginning of the semester. We talked about how each element has a symbol that's either one or two letters, like carbon versus cobalt. That's the symbol, one or two letters. And so C equals carbon, CO equals cobalt. And then A here is the mass number. The mass number is equal to the sum of the protons and the neutrons, because both of those subatomic particles weigh about 1 atomic mass unit, which is way more than the mass of the electrons. So by counting how many protons and neutrons we have total, we're going to figure out how heavy our atom is approximately. The mass number is not equal to the atomic mass, it's just very close. Now we have Z. Z is our atomic number, which is equal to the number of protons. And that's what defines which element we have. So for instance, if we look on the periodic table, carbon has 6 protons and cobalt has 27. Cobalt has an atomic mass of 58.933, and so there's probably different isotopes of cobalt, maybe one with a mass number of 58, maybe one with a mass number of 59, and the atomic mass is a weighted average of those different isotopes. And carbon-12 has different isotopes as well. The most abundant isotope is carbon-12. All right, let's do a quick review problem and try to figure out the symbol for different elements, or otherwise fill in this table with the gaps. So each column here represents a different problem for you to figure out. Go ahead and pause the video and try to figure out each column. Assume that it represents a neutral atom. All right, let's figure this out together. So we know that the sum of the protons and the neutrons is equal to the mass number. We know that it's neutral because it says neutral. And so the number of protons has to equal the number of electrons because it's neutral. Neutrons are neutral. Okay, and we know that the number of protons is equal to the atomic number. So let's figure this out. So based on this symbol here, we have an atomic number of 24. Since it's neutral, that means we also have 24 electrons. It has a mass number of 52. We know that the number of protons plus the number of neutrons is equal to the mass number. So we can subtract 24 from both sides to get the N is equal to 52 minus 24, which is 28. Okay, now on to the second problem. The second problem doesn't tell us the symbol, but it does give us the number of protons. And we know that the number of protons is equal to the number of electrons because it's neutral. Then we can add these two together to get the mass number. So 25 plus 30 is equal to 55. And then we can write our symbol. We have 55 as the superscript and 25 as the subscript. Then we can look at the periodic table to figure out what has an atomic number of 25, and that's manganese. Now let's do the third column. The third column tells us the number of electrons, and so we know that must be equal to the number of protons. And then we know that the mass number is 222. And so 222 is equal to the number of protons, which is 86, plus the number of neutrons. Subtract 86 from both sides. And so N is equal to 222 minus 86, which is 136. And so my mass number was 222. My atomic number was 86. And so looking at my periodic table, what has an atomic number 86? And that's radon. Okay. So I've mentioned the word isotope. So let's try to remember what isotope means. Isotopes have the same number of protons and different numbers of neutrons. That means they will have the same atomic number, so they'll be the same element. That's not it. So they'll have the same element. But they have a different number of neutrons. So if you look at these three element symbols here, can you pick out the pair of isotopes? Go ahead and pause the video and try to pick out the pair of isotopes if all three of these, from the three of these. Okay, so since it has the same atomic number, it needs to have the same atomic number. So our pair of isotopes are these first two. You can tell that they have different mass numbers. They have a different mass number because they have different counts of neutrons in the nucleus. All right, so On this slide, I also want to define some symbols to mean our protons, our neutrons, and electrons. These symbols will help us when we're balancing in nuclear equations. So for our proton, a proton will have an atomic number of 1, which makes sense because that's proton count. Protons contribute to the mass, so it will have a mass number of 1. And we can either write a p, a lowercase p, because we don't want it to look like phosphorus, or we can write an H for hydrogen. So we can write a lowercase p or an H for hydrogen. On ALEX, they'll want you to write an H for hydrogen. So there's that. Okay, so for a neutron also contributes to the mass, but a neutron is not a proton, so it will not have an atomic number. And we'll give it a lowercase n. An E will be used for an electron, similar to how we had E for electron in the redox chapter. Electrons do not contribute to the mass, so it will have a 0 for the mass number. And this might seem weird, but they're going to have a -1 for the atomic number. And that's to help us with balancing our nuclear equations. And that will make a little bit more sense later. Before we dive into too much about nuclear equations, it's good to give a shout out to a famous scientist, Marie Curie, who coined the term radioactivity. Marie Curie won 2 Nobel Prizes, and she was the first woman to win and the first person to win a Nobel Prize twice. And I believe she remains the only person to win a Nobel Prize in 2 different subjects. She has a Nobel Prize in physics and a Nobel Prize in chemistry. Her research on radioactive elements gives rise to a lot of what we know today. She was one of the pioneers in the field. And she discovered radioactive elements, radium and polonium. Polonium was named after her native country, Poland. So when we're talking about radioactive isotopes, we're talking about some isotopes, like a particular isotope of an element, that's nucleus is unstable. And since it's unstable, it will spontaneously decompose into smaller nuclei in an effort to become more energetically stable. This decomposition that happens spontaneously will cause that element to emit radiation of some kind to become more stable. There's different modes of radioactive decay, and we'll go over each of these on subsequent slides. But in Chem 3A, we're going to be focusing on these first 4. Alpha particle emission, beta particle emission, emission of gamma rays, and positron emission. On ALEX, you might see some electron capture problems, but we'll not be focusing on those in this talk. But this is a summary slide that also gives an example of each process. So you can go over this. This is a nice summary slide, but we'll go over each one. As we go over the different modes of radioactive decay, we will be writing nuclear equations. Nuclear equations are slightly different than chemical equations. In nuclear equations, the atomic numbers and mass numbers are conserved. We will use this fact to predict what the product will be, because we can look at the mass numbers and see that that's 238. And then if we add these together, we can see that that adds to 238. Also, the atomic numbers are conserved. So if we look at the atomic numbers, these add to 92, which is the same as over there. We are only interested in the changes occurring to the nucleus, and therefore we are not going to be writing charges on anything. Even though the alpha particle technically would be charged because it's a helium nucleus, we are not going to be writing charges. In nuclear chemistry, we are really focused on the changes happening to the nucleus. That's why it's called nuclear equations. This is in contrast to chemical reactions. Chemical reactions involve changes to the electronic structure of the atom. Chemical reactions involve how are the electrons being shared between atoms? How are they being transferred between atoms? Do atoms gain electrons, lose electrons? It's all about the electrons. In chemical reactions, it's all about the electrons and what the electrons are doing. In chemical reactions, there is no change to the nucleus, and so the number of each element stays the same on both sides of the equation. So chemical reactions, you cannot change a carbon atom into like a boron atom. You have to have the same number of each element on both sides of the equation. It's impossible to change one element into another. That's quite different from nuclear reactions. Since we are changing the nucleus of the atom in a nuclear process, then the identity of the elements may change. And so alchemists used to struggle with this concept of trying to turn lead into gold and make it a more valuable metal. And now in nuclear chemistry, that's a change that might actually be possible. Since we are only interested in the nuclei, we are not writing the charges, but we will be changing the identity of elements. All right, so in the nuclear equation, we got to add up our mass numbers. And so that means that we can use some simple arithmetic to calculate what the identity of the daughter nuclei is. So this is the parent nucleide on the reactant side, and on the product side, it's called the daughter nucleide. So we know that the sum of the mass numbers has to be the same. So 232 is going to be equal to x plus 4. And so if I subtract 4 from both sides, 232 minus 4 is 228. And so x is equal to 228. So I'm going to go ahead and write that as a mass number in the symbol. Okay, and now I have my y and my 2 is equal to 90. And so 90 is equal to y plus 2. Subtract 2 from both sides, y is equal to 88. So my atomic number is 88. And now I have to match this question mark, or match the 88 to the periodic table. And so the atomic number 88 is radon. And so radon would be here to balance this nuclear equation. All right, so our first mode of radioactive decay is alpha radiation. Alpha radiation emits an alpha particle from the nucleus. So here's an unstable nucleus. You can see it glowing yellow, and then it emits an alpha particle. An alpha particle is a helium nucleus. So helium has an atomic number of 2 and a mass number of 4. And then a Greek letter alpha looks kind of like an A, but it's more like written like a kind of a fishy. And so you go down and then cross it to make your alpha. You can practice that. Go down and then around. Alpha, alpha, alpha. So let's figure out what the product is from this alpha decay. So if we had 222 radon with atomic number 88, that's going to be emitting an alpha particle. So one of our products is an alpha particle. We know that the mass numbers add up to 222. And so if I subtract 4 from 222, I end up with 218. My atomic numbers are also conserved. And so 88 minus 2 is 86. And then I can check on the periodic table, and 86 is radon. Another mode of radioactive decay is beta emission. A beta particle is like an electron, but it comes out of the nucleus. In beta decay, how we get that electron to come out of the nucleus, we learned way back in the beginning of the semester that the subatomic particles in the nucleus are protons and neutrons. And so we don't really have a source of electrons in the nucleus. And so what happens to get this electron to come out of the nucleus is that a neutron is going to be turned into a proton. And so let's write a nuclear equation for that process. We have our neutron, and that's going to convert into a proton. And we know that our mass numbers are conserved. And so we emit a particle with no mass. And our atomic number has to be a -1. And this is our electron. It's either written as electron, an E for electron, or a B for beta. Well, that's a Greek letter beta. To make a beta, you should start at the bottom to make a tail, and then you come up and make 2 humps. So up and then 2 humps. Up and 2 humps. Kind of like a bee, but with a tail. So let's write an equation for this beta emission. So if carbon-14 emits a beta particle, then it's going to be emitting something with a mass number of 0, a -1 for the atomic number, a beta symbol, and then I know that these two numbers have to add up to 14 to match that, and these two numbers have to add up to 6, and so this has to be a 7. And then on the periodic table, nitrogen is what has an atomic number 7. The third type of radioactive decay is gamma emission. We learned in the beginning of the semester the electromagnetic spectrum. And so you might remember waves, and the most energetic was gamma. That was more energetic. So high. And then we had X-rays, and down at the other end of the spectrum we had radio waves. So you might remember the electromagnetic spectrum. So gamma rays we've actually seen before as part of our electromagnetic spectrum. Gamma rays are not a particle. They're a particle of light. That's known as a photon. So they're high energy photons of light, but it has no mass. Light just has particle-like properties and wave-like properties. So it's like a particle of light is known as a photon, but it's a high energy wave. It's nothing with mass. It's not like a physical object. Has no mass, has no volume. So has no mass number, and it's just energy, and so it's no atomic number either. This is the Greek letter gamma, and so to make the gamma, you go down. It's kind of like a vertical little fishy. That's a bad gamma, but a lot of times my gammas are a little bit more loopy than that font. But you can make a gamma too. Practice your gammas. So there's my gamma, and I have to write a balanced nuclear equation for this process. Since my mass number doesn't change, these will have to add up to 234. So 234. These have to add up to 90, so that's still 90. And so the identity of the element doesn't change in this nuclear process. Next up is positron emission. Positrons have the same mass as an electron, but they have a positive 1 charge. So that's very strange. We haven't encountered something like that before. But again, this is being emitted from the nucleus of an atom. And so what's happening here is that a proton changes into a neutron. So you might remember in beta emission, 2 slides ago, we had a neutron changing into a proton. In positron emission, we are turning a proton into a neutron. There's some really weird stuff that happens with these subatomic particles. So let's write a nuclear equation for a proton changing into a neutron. So a proton changes into a neutron. That's not a neutron. A neutron has a mass number of 1 and an atomic number of 0. And so these have to add up to 1. And so I'll have a mass or atomic number of 1. And these have to add up to 1. And so a mass of 0. And so this similarly matches our electron symbol. And so we can write a positive 1e, or we can write our symbol for beta with a positive charge to indicate that it's a positive beta symbol. I'm going to opt for the top option. So we have 0 and 1. And so you can use your beta positive, or you can choose your E. And we know that these are going to have to add up to 90. And so this is going to be 89. These have to add up to 234. So the mass number is going to stay the same. And so looking at my periodic table, actinium has our atomic number 89. So some students might be wondering, how will you know what mode of decay your element will undergo? Like, how can you predict that? That's going to be more of a Chem 1A topic, but it's still very interesting to understand why some elements undergo beta decay and others undergo positron emission or alpha decay. So we saw in beta emission that our atomic number went up. And so in beta decay, like our beta negative, the negatively charged beta particles, our atomic number increases. And in positron emission, our atomic number decreases. And so if we graph what our stable nuclei's atomic number versus our stable nuclei's mass number, atomic mass, then we find that if we had our number of neutrons on the y-axis, number of protons on, this is really the number of neutrons. If they were a 1-to-1 ratio of protons to neutrons, it would be this red line. And so this red line represents number of neutrons equal to the number of protons. And you can see that the actual stable nuclei are a little bit more than that. So it starts off as a 1-to-1 ratio of protons to neutrons. But as the atoms become larger and larger, you need more neutrons to pad the protons for your elements to be stable. And so those neutrons are padding around the positive charged protons. Positive charges don't actually want to be next to each other. So that's there. Those are the stable ones. And so if you're outside of that stable region, then you're going to try to move closer to that stable region. And so elements over here, I'm going to try to move that way by increasing their atomic number. And elements that would be here are going to try to move that way closer to the band to decrease their atomic number. All right, practice writing some nuclear equations for each of these processes. Remember that this notation refers to the mass number of that element. Go ahead and pause the video and try to write nuclear equations for each of these processes. Okay, let's go over this. So this says alpha emission from uranium-238. So we have uranium with a mass number of 238. If I look on the periodic table, uranium has an atomic number of 92. It's alpha emission, and so that means that my product is going to be an alpha particle, and I should balance my equation to find out what my daughter nuclide is. These two are going to add up to become 92, and my mass number needs to add up to become 238. So 238 minus 4 is 234. And then my atomic number would be 90. Atomic number 90 is thorium. Okay. Next up, we have beta emission from neon-24. Neon has an atomic number of 10, and we have a mass number of 24. And so I need to emit a beta particle, which is like an electron from the nucleus. And this has to add up to 10. And so my atomic number is going to be 11. And the mass numbers have to add up to 24. And so my mass number is 24. And so sodium has an atomic number of 11. Next up, we have gamma emission from nitrogen-13. Nitrogen has an atomic number of 7. It told us the mass number was 13. It's emitting gamma radiation. that has to add up to 7. These have to add up to 13. And so there is no change to anything because it's gamma radiation. All right. There are more complicated nuclear equations possible. In addition to nuclear decay, there's also nuclear fission and nuclear fusion. Nuclear fission involves splitting a nuclide into smaller nuclides. So here's a neutron being slammed into uranium, and that's going to split it apart into krypton and barium, and a lot of energy is released along with 3 neutrons. So this is also a nuclear equation for that image above. And if you pay attention to the mass numbers, you can see that the mass numbers are conserved. You can have a coefficient. So if you have 3 neutrons, then that becomes a 3 coefficient for that particular item. But that just means you have 3 times 1, and so that represents you have a total of 3 neutrons there. So the mass number would be a total of 3 when you're adding up your items. And so we also have nuclear fusion. Nuclear fusion is when 2 lighter nuclei fuse together to make a heavier nucleus. And the sun is an example of a giant fusion reactor. There's a song by They Might Be Giants where they sing about the sun. It's a really fun song. You should listen to it. Okay, so here's a practice problem for you, and you should balance this equation. Pause the video and try to balance this nuclear equation and find out what the missing piece is. Okay, so let's work this out. We know that our mass numbers have to add up to be 5. And so the sum of these 2 items has to be 5. And so my missing mass number must be 4. My atomic numbers add up to be 2. And so my atomic numbers have to add up to 2. And so then I can look at the periodic table and see what has an atomic number of 2, and that's helium. And so this is the reaction that happens in the sun. Hydrogen is burned into helium at a temperature of millions of degrees.